Recording now.
Recording right now?
I am now.
Did anybody watch the video?
Shh.
Could you go into my phone?
Yeah. Okay. 6.5, polar graphs, roses take the form of R equals A cosine of n theta and A sine n theta. And that n is actually included inside the sine function. Okay? You can't divide by n. Well, not that you're going to have the opportunity to do that, but if something is inside with the angle, the only way to get rid of that, or to get to n, is to take the inverse sine or inverse cosine of something. And for what we're doing with this, you're never going to need that. Okay? Your goals today are as follows. I'm going to give you an equation like this. I'm going to expect you to be able to graph them. If I give you a picture of the graph and the equations, can you match them up? Okay, so going both ways. If you have the equation, can you match the graph? If you have the graph, can you match the equation? Okay. The rows is the most complicated. The other two are fairly easy. It actually gets easier as we go into the lesson today. So we're going to hit the hard part first. It's just a lot of details. How many petals does it have? What kind of symmetry does it have? All that's based on A and n, and whether it's sine or cosine.
Is n the number of petals?
Almost. Okay? It has something to do with that. Okay? N has to be greater than 1. Based on the number of petals, this is how it works. Right? And so n's going to be bigger than 1, just guaranteed. If n is odd, then yes, n tells you exactly how many petals it has. If n is even, you double n to tell you the number of petals. So this is useful for when I have an equation and I have 6 graphs and I got to match up the graph. Well, if I can simply identify the number of petals, then I can just simply mark off the ones that don't have that right number of petals.
So if n equals 1, then there's 1 petal.
N won't equal 1.
Oh.
It must be greater than 1.
Going to have it. Minimum number of petals is 2. Well, actually, it's 3. Because if n was 2, what would I have? You'd have 4 petals. Because you double it if it's even. So I'm going to have 4 petals. The minimum is 3 petals total. What? I'm not exactly sure. That's a good question. I think it's because you got sine and cosine can occur twice, positive places, and twice for negative places. So when I plug it in, you get 2 varieties for each one. But that's not necessarily the right explanation. All right, next thing. Petal length. Okay? Petal length is determined simply by looking at the absolute value of A. Now, A can be negative, A can be positive. You're talking about reflection over the x-axis if A is negative. Literally, flip it upside down from the way we talk about graphing it. Okay? The next thing we're going to talk about is symmetry. There are a number of things that can be symmetric about these graphs. There's 3 varieties of symmetry here, and you have to determine which graphs have which symmetries. You can have x-axis symmetry, you can have y-axis symmetry, and you can have point symmetry around the origin. So I can spin it 180 degrees, and I get the same picture as I started with. Okay? X-axis symmetry means we fold it over the x-axis, and you got the same thing on top and bottom. Y-axis symmetry means I can fold it over the y-axis. I got the same picture on the left and the right. Exactly the same. Okay? It's very easy to see that kind of symmetry from the picture. So I'm not worried about you telling me about the picture. I'm worried about if I give you the equation, can you work backwards and tell me the type of symmetries that it has?
So y is just an even graph and point symmetry is just the point graph?
Yeah, that's exactly right. Good. If n is even, then it has all of the symmetries we talked about. Okay? So, to make your job easy, if you're looking at sine or cosine, and you're looking at the n, and your n is even number, all the symmetries. Symmetric over the y, symmetric over the x, symmetric around the origin. If n is odd, well then you're going to have to pay, this is where you're going to have to pay attention. Okay? It's going to depend on whether you have sine or cosine. It's going to depend on the type of symmetry it gets. So cosine, it's across the x-axis, and sine is across the y-axis. But that makes it super easy to remember because go back to your unit circle. Cosine was what? Was x, and sine was y. So you see lots of things beginning to repeat themselves. Things that kind of reoccur and show you the relationship isn't just in one scenario. It's true across the board. Okay? Other questions? Okay. Nothing. Let me take a minute and I'm so horrible at drawing these things. Yeah, these are terrible. So if I were to draw, let's say we do 2 sine. Let's do cosine, it's easier. 2 cosine of 3 theta. Let's suppose we can draw that one. Well, let me just ask you some details first. How long are the petal lengths? They're going to be 2 units long. How many petals am I going to have? 3. Now, here's something to note. So make somewhere around cosine, right there, or maybe make a new section on graphing. Cosine, the first petal you're going to draw will be on the x-axis, the positive x-axis. So I'm going to go down here, and I'm going to draw 1, 2.
How do you draw a petal?
More like a leaf, actually.
I see.
Okay?
This is the first example?
Yeah.
How do you know that it's 2?
I'm telling you right now. It's units, 2 units long because A is 2 in my equation. 2 cosine 3 theta.
So it's always up or down?
Well, whichever petal falls on the axis,
Wait, isn't it even? Don't you have to double it?
3 is odd.
Oh, it's the number.
N is odd. That tells you the petals. A, the part out front, tells me how long the petal is. Okay. The number beside theta is N. That's going to tell me how many petals there are.
Can they ever change how wide they are?
I don't think so. I think that depends on the. It's uniformly distributed around it, so it'll get wider in the middle and come back. So the longer the petal gets, the wider it gets. Okay. When you're graphing this, it's really nice to know exactly around where does that petal occur. If I have 3 petals, and these things are exactly 360 degrees, in other words, they're going to repeat themselves no matter how far you go around the circle. How far between each petal do you think I'm going to have?
Oh, I was so close.
120 degrees between each one. So I'm going to make a mark just to kind of help myself remember it. So that's about where the other petals are going to, the tip of each petal is going to be. So I'm going to use that to kind of help we're talking about very rough estimates here. I don't need, yeah, that was awful.
So is that what you do every time?
Yep. Thanks, Trey. Appreciate that. Felt the love on that one. And so now, and my isn't perfect, but you get the idea. Let's go back to symmetry. This is cosine. It's odd. So I have x-axis symmetry. Do I have x-axis symmetry in that particular graph? Yes, we do.
Is that how you know to draw the third petal down there?
Well, I know to draw the first petal on the x-axis, and then I use the angle, I divide it up equally to figure out how many times around. Sine's a little bit different. Okay? Sine, if we look at the sine graph, I'm going to let you do some in a minute by yourself. Sine starts, listen to me carefully, sine is going to start on the y-axis, either at the bottom or the top. Here's how you know. If it's 3, if it's sine of 3 theta, you start at the bottom. It's going to alternate thereafter. So if it was sine of 5 theta, you'd start at the top. Sine of 7 theta, start at the bottom.
What?
Okay? You'll see. Watch. Shh. Let's do an example. Let's do the next example.
I thought this. What if it's even?
Okay. Here we go. I want you to give your best shot. Do the cosine one first, since we just did a cosine. This one will be pretty straightforward. Okay, you'll do the cosine just like we did. It's odd, so you know it has x-axis symmetry. It's going to have a petal length of 3. It's going to have 5 petals. Because it's cosine, I start on the positive x-axis. And you'll have to determine the angles between them, kind of dividing that by 360. Or 360 divided by your n. Sine, different. And as far as your first petal that you draw, that's the one I'm going to be looking at for the length. Thereafter, you can kind of give me a good estimate, especially if it's diagonal. It's not going to be real easy to find it if you're getting the right exact length. Just be close. I'm not really looking for perfection. They won't overlap. Well, they shouldn't. What do you mean overlap?
Like the next one's like that. Can they overlap?
No.
Ah.
72. Just start here and go right. Yep. Your petals should not overlap each other. How far apart are the petals going to be? Here. 72 degrees. So 72, then add 72 to get 144, then add 72 again, then add 72 again. If you add 72 again, you're going to get back to 360, back to where you started from. It's close. Like 144, it's well into the second quadrant. So it would be, just, if you kind of know where 120 and 150 is, just get close. I mean, I definitely didn't measure on this thing. Okay.
For theta, would you just put x?
No, when you have to change it to polar, go to mode, change it to polar, theta becomes x in polar form. Now, for sine theta pi of 3 theta, you've got, looks just like this. Remember, sine, if it's 3, we start drawing it at the bottom. And then we're going to go up. We know that it's got 3 petals. We know that they're 120 degrees apart. So I don't use the actual angle. I just say make sure I'm 120, then 120, then 120 to go around that circle to get back to where I started from. What if this had been 4 sine 5 theta? How would we do that? What would change about this? 4 sine 5. In other words, I have 5 petals, of course. Where would I start to draw the petal? 5. I would start at 90 degrees and draw the first petal straight up and then go around the 72 degrees. It would look just like, it would look just like my petal that we have right here for 3 cosine 5 theta, but it would be just rotated a little bit.
And how do you know? I'm screwed. How do you know?
Well, it'd be longer too.
And y-axis?
Okay, one more time. Sine starts off, remember, 3 is the smallest number of petals we can have. It starts off as 3, and it's straight down. So you draw your first petal at 270 degrees. At 5, if I have 5 theta, I would start drawing at 90 degrees. At 7, I go down. At 9, I'm back up. So it just alternates every other one. So it's 3, 5, 7, 9. Remember, if it's even, that's easy. It's just you divide it up evenly across the space. Remember, it's symmetric about the x, the y, and the origin axis. Okay? So it would be perfectly symmetrical when you do even numbers. Okay? And depending on how many there are, remember, sine, if sine is even, you will have no petals on any axis. Okay? If cosine is even, you will have 1 petal beginning on the axis, and depending on how many there are, you may have more on the axes or off the axes, but it'll be symmetric. If one of them is on the axis, chances are they're all on the axes. Okay? Or it may be every other one, but it'll be symmetrical.
You have 4 theta, why can't you do it on every axis?
Well, it could be on 4 theta of sine or cosine. Cosine would be on every axis. Sine would be in between the axes. So it would be on the 45 degree angles. Okay? 5, 7. Mhm. Yes. Here we go. Let's change it a little bit. That says limaçon. Shh. It's actually, no, I don't know what language that is.
Jamaican.
The C with the little tail on it is pronounced ks, and so it's limaçon.
Limaçon.
So if you don't have to do the ks. I think is it Portuguese? Or maybe it's something from Latin probably. Man.
What is all this used for? Because, like, you know how the other thing was, like, used for navigation and stuff?
I'm not really sure why you would do this. I'm sure they're in art has some applications.
Because someone felt necessary that.
I don't know enough. I haven't used this enough to give you a good explanation. That's an equals. I change it here in a little bit.
Wait, how do you spell it?
Just draw C.
Okay, this is called a limaçon. Limaçons actually have a bit of a strange shape to them.
No way.
What I want you to walk away from this with is, if I give you the equation based on A and B, I need you to identify the shape of the graph. We have 4 different shapes. Okay? A plus B has to be greater than 0. So we have what's called a loop, a cardioid, a dimpled limaçon, and we have the last one, which is convex limaçon. All of this is based
How do you say
on
the second one? Cardioid?
cardioid. Cardioid. Cardioid, what's cardioid? You makes you think of a heart. It actually looks somewhat like a heart. If you're a musician, if you know anything about music tech, then most traditional microphones have a cardioid pattern to them. And so it looks just like a heart. Sure. No. Not the shape of the microphone, but the way that it picks up sound is in that pattern. So if you have a microphone like this is the microphone. If you're standing directly behind it, it's not going to pick up your voice, at least not very well. But if you were standing to the side or anywhere around the next part in this kind of vicinity, then it will begin to pick up your voice. So anywhere in this range, it picks you up. But once I step out behind it, there's no sound. And so I'm going to move all that up and show you exactly what the shape is. It says dimpled. Pimple. Y'all are funny. Haha. Okay. I apologize for my very poorly drawn items. Yep. Okay. Shh. This is your loop, clearly defined by the little loop inside the actual shape. Okay. The cardioid looks very similar to that, but instead of, it looks like a heart. It has a very prominent indentation in one side of it that comes to a point. Okay? So it looks similar to a heart. That's why it gets its cardioid name. The dimple is going to have a very slightly, it won't be a point, but it'll go in and back out. And so it's going to look more like, actually, let me do that better.
Dimples?
It's not, the heart goes all the way back to the origin. This one's not going to be as much. But it's just got a point, it doesn't go, it's not as prominent as the dimple. And then the convex has no point at all. It's almost flat on one side. So if you were to kind of draw it, it looked something like this. It's not exactly a circle because this part is actually flat. So now instead of going inside, it's now just flattened. So, no. Let me redraw it so it's a little more prominent.
Just draw one side. Yeah.
I'm exaggerating that flatness a little bit. It's not as pointed as around the curves, but There is no dimple at all in this one.
No dimple.
Okay, so let me tell you how to kind of go about looking at these. Number one, the loop, easiest of all to determine. If I divide A divided by B, in other words, if B is bigger than A, I've got a loop. If B is larger than A, we have a loop. If A and B are exactly the same number, we have cardioid. If we have, when I divide A over B and I get a value larger than 2, in other words, if A is twice as big as B, or more in fact, then you have convex. If A divided by B is between 1 and 2, in other words, if let's say that B was 5, if A falls anywhere between 5 and 10, then you're going to have a dimpled limacon. You know, right? So that's kind of the way you identify these. It's not really about, I'm not really concerned that you draw these so much, but I need you to identify their name, their shape, when I give you a picture, or if I give you an actual equation. Okay, let's go back and add this. Under the convex limacon, make sure that you add the equal to part, because if it's equal to 2, what that means is the thing is stretched out enough to remove that dimple period, and you've now got a smooth surface. Okay? It's not a circle. It is not perfectly uniform all the way around. Okay? It just doesn't have that little insert on the side of it.
Do you have any batteries?
No, I don't. Let's go back to our example. What about this one? R equals, so this was loop.
What if it's less
Okay.
than?
It should be a
I mean minus.
R, it's a good question. She says, what if it's negative? It can't be negative. A and B are always positive.
Then why is it there?
Because the negative is built into the problem. It's not A or B. Okay, so for example, here's a good problem to look at. You have R equals 3 minus 3 sine theta. This is a cardioid. Because A and B are equal, you don't look at the sign. Now the sign's going to be determining, is this going to be down or left or right? Can somebody want to tell me what kind of symmetry this one has? Just guess.
Why?
Why? Why would you say that? Because it's sine, and you're actually correct. Okay? Because we have a 3, okay? No, it's just 3. A and B are the numbers that you see. The negative sign, if there is one, is part of the problem. You're not. It doesn't apply to that 3. A and B are always going to be positive, so don't get confused with that.
No, that's what I was talking about. What if there's minus?
Like right there, it's look at just the numbers, just A and then the B. The minus sign is part of the formula.
All right.
All right, let's go back and do one more type of graph. Shh, here we go. Lemniscates. Lemniscates. Lemniscate. Lemniscates.
Lemony snickets.
Vamos a ver. Entonces vamos a hablar. Vamos a hablar en español toda la clase. ¿Sí? Entonces.
It's a Thursday.
Es jueves.
Morning. Almost 2 o'clock.
Here we go. Shh. Lemniscates are very, this is probably the one that we're going to do the least amount of exposure to. I need you to know the shape. I need you to know how long the petals are, because this graph really doesn't change shape. It can change size. It can rotate. Okay, but it's very limited in what is possible. First of all, look at what's in front of theta. It's a 2. It's not an n. It doesn't change. 2 is built into the problem. Okay, because it's n, we have 2 petals only. This one's a little bit different. If you want to know the shape, this looks just like an infinity symbol. Okay, good practice. It's two pedals on either side.
Will it ever be over the y-axis?
Lemniscates can be vertical, but here's the trick. A lemniscate must remain symmetric to the x, to the y, and to the origin, all at the same time. Because we're limited in the way it can work, then we're limited in the amount of rotation it can go through. We don't have N here, so we're not going to be changing the pedals. There's only two pedals. So if the only piece of information that you need to know about this is that it has specific pedal length. Shh, listen. You have the square root of A equal to your pedal length. So if A is 4, then my pedal length would be just 2. Okay, A is the number out front.
Is it before you square?
No. Oh, I see what you're saying. We'll just say A then. It's the. I'm almost thinking it's the square root of the number that's in front. So
Square root of A squared.
I'll show you an example in just a minute.
So like, it's just A.
So I'm just going to write A. So here's an example. We have r squared equals 4 cosine of 2 theta. How long are my pedals?
Pedals are gonna be
4, 2.
Square roots of A is what? A squared is. I know.
No, let's just write square root.
Hold on. This is A squared. A equals 2. So basically, what I was trying to get the idea out was square root the number in front of the cosine of the sine. That'll get you your pedal length. Okay? I don't need to actually pedal length. Most of the time it will be, yeah. But if I had 5 there, then it would be square root of 5. It would be a decimal. That's possible. Okay? So, shh, listen. That's about all I really need you to walk away from this with. I do want to talk about your calculator for a second. Your homework is going to consist of kind of what we did in class. I want you to go through it's 3 through 12 all. It's going to be graphing some of the rows functions. It's also going to be looking at some of the pictures and identifying which equation matches with which graph.
The graphs don't have to be accurate, right?
The graphs have to be accurate in terms of the number of pedals. I need to see at least on one pedal the length of the pedal, whichever one hits an axis. Or you have to give me that idea. I draw it in there or not.